And we proceed now to the next presentation by Vera Turkova from Samara on nonlinear analysis applied to damage.
Thank you. Good morning, dear colleagues. I am from Samara National Research University. As you know, nowadays failure and damage are of critical interest to designers. While number of composite materials in the industry rapidly increases, there is a lack of damage analysis and failure prediction. For efficient design, it is necessary to have an accurate both analytical and numerical material model. Critical to this is thorough understanding of damage mechanisms and their interactions. Especially on the early stages of structural design, there is a need for a more quick way of estimating material behavior. Engineers must be able to predict the strength of the future structure element and the whole design. Though numerical modeling of such materials possesses several challenges, there is a need for a material model coupled with damage evolution law. Kachanov and Robotnov in their pioneer works proposed continuity and damage parameters for the mathematical description of damage evolution processes. Since that time, damage accumulation equations have been developed, and nowadays many works describe mutual influence of stress-strain state of structure and damage accumulation process near stress concentrators. We can divide the whole continuum damage mechanics into three directions. The three big groups. First group is damage evolution equations, taking into account some states of damage accumulation. Another group is material models for anisotropic damaged materials, and the third group is asymptotic solutions for coupled elastic damage, plastic damage, and creep damage problems. To elucidate the effect of damage accumulation in real conditions and in real structures, we have to apply finite element method to the cracked specimen under mixed loading. In our work, we used damaged material model based on continuum damage mechanics. This model was first proposed by Dubé and Decker and others in their works. The model is the advantages of this model is that it is rather simple, it is reliable, it is verified, and nowadays it is widely used. The initial material, undamaged material, considered to be isotropic and elastic. The stiffness degradation caused by accumulation processes is simulated by adding damage tensor into the equations, material constitutive equations, which was proposed firstly by Sun and Khalil in 2004. Damage tensor components are the functions of stress state, and damage parameters follow the linear evolution law. Here it is. Sigma threshold is the temperature-dependent threshold stress, and sigma critical is the temperature-dependent critical stress. The whole constitutive equations you can see of the material you can see in the slide. In order to carry our calculations, we use Simula Abacus. Abacus provides a wide spectrum of user subroutines, which allow us to adopt the standard program for particular needs of our problem. To define any complex material which cannot be found among standard Abacus materials, we use user subrouting, which is called UMAT, user material. It is a flexible and rather powerful tool for analysis. The SDV, solution-dependent variable, is a value which is calculated during the analysis and used after that in the results. In our particular work, the example of SDV is damage parameter. And together we have the user subrouting and apply it to different specimens. First of all, we took the simplest structure we could think of. It is the 3D elastic rod, which is rigidly fixed at one end. It is loaded in direction. It is subjected to uniaxial load in direction 1. In the upper part of the slide, you can see stresses in the model without UMAT. It is a standard Abacus model elastic material. And in the lower part, there is stress in the model using UMAT. We didn't add some difficulties in the model because we wanted to compare the results of standard material and the material UMAT. It is seen from the results from the finite element analysis that damage accumulation affects on the stress-strain state of the model. Because values of equivalent stress and values of stress-tensor components without using UMAT are considerably lower than with UMAT. Then damage distribution. Damage distribution of each component was also found. You can see it on the slide. And what is interesting, they are characteristically similar with the main stresses, the distribution of the main stresses in the model. The second structure was also simple. It was a 2D elastic plate with a central crack. Here we can see the opposite feature because material stresses in the model with UMAT are considerably lower than stresses in the model without UMAT. These are the components S22. In our example, we see that Let's try to think. So, in conclusions, some numerical simulations were obtained by finite element method combined with user material. The geometry of the active damage zones in the vicinity of different stress concentrators were studied. As stress concentrators, we saw a notch, a crack, and a hole. We see that tension of damaged structures and undamaged structures differs. In perspective, we are going to study evolution of damage accumulation process in time, and it is we have an idea of studying cyclic loading of damaged structures.